In this video, we're going to solve the classic boundary value problem, y double prime plus lambda y is equal to 0, with the boundary conditions y of 0 is equal to 0 and y of L is equal to 0. These boundary conditions are called Dirichlet boundary conditions. Let's think about the physical meaning of this problem. Imagine a piece of string tied down at both ends or boundary points x is equal to 0 and x is equal to L. The solution to this differential equation is y, and it's just the height of the string at every point between x is equal to 0 and x is equal to L. Our goal in solving this problem is to find a non-trivial solution, basically just a function y of x that isn't 0 or a flat piece of string. These non-trivial solutions are called eigenfunctions. The specific value of lambda that makes this non-trivial solution possible is called the eigenvalue, and it's crucial because it determines the frequency of the vibration of the string. Let's now walk through the solution to this boundary value problem. That's this problem right here. And we're going to consider three cases. The first case, lambda is going to be negative. The second case, it's going to be equal to 0. And then the third case, which is the most interesting case, is when lambda is greater than 0. Let's start with case 1, where we're going to assume that lambda is negative. To make the algebra easier, it's customary to let lambda be equal to minus alpha squared. And we'll just remind ourselves that this is less than 0. We'll plug this in and we get y double prime minus alpha squared y is equal to 0. This is a second order constant coefficient equation, so the solution to this equation is going to be of the form y is equal to e to the mx. Let's plug this into our equation. If we take two derivatives, we get m squared e to the mx, and then we subtract off alpha squared times e to the mx, and we'll set that equal to 0. Let's factor out e to the mx, so we get m squared minus alpha squared times e to the mx is equal to 0. Our exponential function is always positive, so that means that m squared minus alpha squared has to be 0, and this gives us that m is equal to plus or minus alpha. We can now write down the solution as y is equal to c1 e to the alpha x plus c2 e to the minus alpha x. There is another way that we can write this solution, and it looks like this. So let's just put a little or here. Y is equal to c1 cosh of alpha x plus c2 times sinh of alpha x. Just for review, I've written down over here on the right what sinh is equal to and what cosh is equal to, and I included their graphs. Let's now find C1 and C2. We're going to use the boundary conditions to do that. Let's find y at 0. That is going to be C1 times cosh of 0. Cosh of 0, if we look over here on our graph, is equal to 1. So we'll put a 1 here, plus C2 times sinh of 0. Sinh of 0 is equal to 0. And if we look back up to the top here, we see that y of 0 is equal to 0. So we'll set this equal to 0, and that tells us that C1 is equal to 0. We now have that y is equal to C2 times sinh of alpha x. Now we can find C2. We'll use our other boundary condition to do that. And that says that y of L is 0, so we're going to let x be equal to L. This is C2 sinh alpha times L, and that's equal to 0. Let's look back up at the top. We have that lambda is equal to minus alpha squared, and that's less than 0. So this means that alpha cannot be equal to 0. And we know that L is the right boundary point, and that also is not equal to 0. So the only solution to this is that C2 has to be equal to 0. And this gives us the solution that y of x is equal to 0. This is called the trivial solution, and it means physically that the piece of string that lies between 0 and L is just flat. Let's now go to case 2. In case 2, we're going to assume that lambda is equal to 0. So we let lambda be equal to 0, and this gives us the equation y double prime is equal to 0. To solve this, we are going to integrate both sides. On the left, we get y prime, and then on the right, we get a constant that I'll call C1. Now we're going to integrate again. We have the integral y prime dx is the integral C1 times dx, and this gives us that y is equal to C1x plus another constant that I'll call C2. Now we can use our boundary conditions to find C1 and C2. We have y at 0 is equal to C1 times 0 plus C2, and that's equal to 0. So this tells us that C2 is equal to 0. So this gives us y is equal to C1 times x. Now we'll use our second boundary condition, which is y of L is equal to 0. So we have y at L is equal to C1 times L is equal to 0. And this means that C1 has to be equal to 0. This gives us the solution that y of x is equal to 0. And just like in case 1, this is a trivial solution. Let's now look at case 3. This is the interesting case because we're finally going to get a solution that is not the trivial solution. In this case, lambda is assumed to be positive. And again, for algebraic convenience, we're going to let lambda be alpha squared, and that's greater than 0. Let's plug that in. We have y double prime plus alpha squared times y is equal to 0. Again, we get a second order constant coefficient equation, and we can assume that y takes the form of e to the mx. Plugging this in, we get m squared e to the mx plus alpha squared e to the mx is equal to 0. This gives us m squared plus alpha squared e to the mx is equal to 0. The exponential is not equal to 0, so we have to set m squared plus alpha squared equal to 0, and this gives us that m is plus or minus I times alpha. We then note that our solution looks like this. Y is equal to C1 cosine alpha x plus C2 times sine alpha x. Now we're going to find C1 and C2. We'll first use the boundary condition that y of 0 is equal to 0. So we have y of 0 is C1 cosine of 0 is 1 plus C2 times sine of 0, that is 0, and that's equal to 0. So this gives us that C1 is equal to 0. We now have that y is just C2 sine alpha x. We can find C2 by using our second boundary condition. We're going to let x be equal to L, so we have y of L is C2 sine alpha L, and that is equal to 0. There are two ways that this expression can equal 0. The first way is when C2 is equal to 0. Just like case 1 and case 2, when we let C2 be equal to 0, we get that y of x is equal to 0. So we get the trivial solution. So that's one solution. However, with this case, we have more solutions that are much more interesting. The second type of solutions we're going to get is when we set sine of alpha L equal to 0. Sine is going to be equal to 0 when alpha L is equal to n times pi. We'll talk about what n is equal to in just a few minutes. This gives us that alpha is equal to n pi divided by L. Let's go back up here and let's look at this expression right here. Lambda is equal to alpha squared. So we have lambda is alpha squared, and that tells us that lambda, remember that is our eigenvalue, it is equal to n pi divided by L quantity squared. Since n is squared, we can just say that n is equal to 1, 2, 3, and all the integers after that. I didn't include that n is equal to 0 because that's our trivial solution. Let's go ahead and let's highlight this. There's our eigenvalue. And notice, because of all the values that n can take on, that we have an infinite set of eigenvalues. Let's now look at y of x. We have that y of x is equal to C2 times sine of alpha times x, and alpha is now n pi over L, and there's our x. When we are solving this type of a boundary value problem, we really want to focus on the shape of y and not the amplitude of y. So I am going to choose to let C2 be equal to 1. This gives us that our eigenfunction y of x is sine n pi x over L. Remember, the eigenfunction is the solution to the equation that is a non-trivial solution. This value of y is an eigenfunction, but this value of y is not an eigenfunction. Let's talk for just a minute about frequency. The angular frequency of our function y of x is going to be n pi over L. That's just whatever multiplies the x. And n pi over L is the square root of lambda. So we can say that the angular frequency is the square root of lambda. Let's now see what these eigenfunctions look like. In the green curve down here, I've plotted the solution y is equal to sine pi x over L because n is equal to 1. This is called the fundamental mode, and it is the lowest frequency of vibration. The purple curve is when n is equal to 2, and this is called the second harmonic. And then the blue curve is when n is equal to 3, and that's the third harmonic. By solving this boundary value problem, we found the different shapes that our solution can take on. Those are the eigenfunctions, and then the natural frequencies associated with each shape, and those frequencies are related to the eigenvalue lambda. And that's it. You should now be ready to work through similar problems with different boundary conditions because the method for solving the problem stays the same. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.